Hello. Welcome to Lesson 2. This is the second lesson of a set 8 lessons on the field of algorithmic thinking. In the previous lessons we saw what is logical thinking. In this lessons we are approaching the notion of algorithmic thinking. This lesson duration is about 75 minutes. We organize the trainees to a group of maximum 15 persons. For the lesson we will need a projector, a questionnaire and a personal computer or laptop for the trainees. The objective aim of this lesson is to teach trainees the importance of logical thinking. An algorithm is a set of step-by-step procedures, or a set of rules to follow, for completing a specific task or solving a particular problem. The word algorithm was first coined in the 9th century. Algorithms are all around us. Common examples include the recipe for baking a cake, the method we use to solve a long division problem, the process of doing laundry, and the functionality of a search engine are all examples of an algorithm. Here's what baking a cake might look like, written out as a list of instructions, just like an algorithm. Route ND. 1. Preheat the oven. 2. Gather the ingredients. 3. Measure out the ingredients. 4. Mix together the ingredients to make the batter. 5. Grease a pan. 6. Pour the batter into the pan. 7. Put the pan in the oven. 8. Set a timer. 9. When the timer goes off, take the pan out of the oven. 10. Enjoy. Algorithmic programming is all about writing a set of rules with a finite number of steps that instruct the computer how to perform a task. A computer program is essentially an algorithm that tells the computer what specific steps to execute, in what specific order, in order to carry out a specific task. Algorithms are written using particular syntax, depending on the programming language being used. Algorithm properties. The definition of an algorithm is complex and involves several properties. This subsection describes those properties. Collection of individual steps. The first property to mention just restates something said earlier: an algorithm is a collection of individual steps. A recipe fits this analogy quite simply, filled as it is with steps like, preheat the oven to 180 degrees Celsius or add 2 tablespoons of sugar to the bowl. Definiteness. Following on from that property is definiteness, meaning that every step must be precisely defined. Each step in an algorithm can have one and only one meaning, otherwise it is ambiguous. Similarly, chefs have come to the same conclusion, which is why they produce recipes using precise measurements instead of writing things like some sugar or cook it for a while. Sequential. Algorithms are also sequential. The steps that make up the process must be carried out in the order specified. Failing to do this means that the result of executing the algorithm is likely incorrect. Think back to the analogy. Dicing an onion and frying an onion are different steps. Dicing an onion before you fry it has a different outcome than the reverse. Similarly, multiplying a number by 2 then adding 5 to it yields a different result from adding 5 first then doubling it. Like a recipe, you must respect the sequence when running through an algorithm for it to have any meaningful result. Detour, state in algorithms. It's worth going on a brief detour here to examine why sequence is so important to algorithms. It's all to do with state, by which I simply mean the current values of all the things the algorithm is keeping track of. As a computer progresses through an algorithm, just as you progress through a recipe, the state of things can change. Clearly sequencing the steps of an algorithm ensures that state always changes in the same way whenever the algorithm is executed. Types of algorithms. Algorithms are classified based on the concepts that they use to accomplish a task. While there are many types of algorithms, the most fundamental types of computer science algorithms are divide and conquer algorithms. Divide the problem into smaller sub-problems of the same type, solve those smaller problems, and combine those solutions to solve the original problem. Brute force algorithms. Try all possible solutions until a satisfactory solution is found. Randomized algorithms. Use a random number at least once during the computation to find a solution to the problem. Greedy algorithms. Find an optimal solution at the local level with the intent of finding an optimal solution for the whole problem. Recursive algorithms solve the lowest and simplest version of a problem to then solve increasingly larger versions of the problem until a solution to the original problem is found. Backtracking algorithms divide the problem into subproblems, each of which can be attempted to be solved. However, if the desired solution is not reached, move backwards in the problem until a path is found that moves it forward. Dynamic programming algorithms break a complex problem into a collection of simpler subproblems, then solve each of those subproblems only once, storing their solution for future use instead of recomputing their solutions. Sorting algorithms. A sorting algorithm is an algorithm that puts elements of a list in a certain order, usually in numerical or lexicographical order. Sorting is often an important first step in algorithms that solves more complex problems. There are a large number of sorting algorithms, each with their own benefits and costs. Below, we will focus on some of the more famous sorting algorithms. Linear sort: find the smallest element in the list to be sorted, add it to a new list, and remove it from the original list. Repeat this until the original list is empty. Bubble sort: compare the first two elements in the list, and if the first is greater than the second, swap them. Repeat this with every pair of adjacent elements in the list. Then, repeat this process until the list is fully sorted. Insertion sort: compare each element in the list to all the prior elements until a smaller element is found. Swap these two elements. Repeat this process until the list is fully sorted. Examples of real-world algorithms. Whether algorithms are used in places that aren't at all surprising, like Google, or in a manual activity that is more unexpected, like brushing your teeth, algorithms play a role in the human experience every single day. Below, we present some examples of everyday algorithms. 1. Sorting papers. Imagine a teacher sorting their students' papers according to the alphabetical order of their first names. This type of task is similar to the function of a sorting algorithm, like a bucket sort. By looking at only the first letter of the first name, you can remove a lot of unnecessary information. This is an automated process that makes sorting more efficient. 2. Facial recognition. Every day we see someone we know, a loved one, a coworker, or even an eccentric neighbor. When we recognize somebody's face, we're drawing upon data we've previously collected on the size and position of that person's facial features. That information is then analyzed internally to automatically recognize others. Google search. Even an action as seemingly simple as a Google search is only possible with the help of algorithms. Say, for example, you want to know if an elephant can swim. How you phrase the question to Google is the input you are asking the computer to determine. Google doesn't even need all the words of the question "Can an elephant swim?" For example, try searching for swimming elephant and see what you get. You will find that immediately, the output or the results show videos of elephants swimming, followed by more on the subject. Google uses an algorithm to generate these answers without needing the entirety of the question. Traffic lights. Traffic lights are a great example of how algorithms are used in the real world, all around us. Most traffic lights don't automatically cycle through green, yellow, and red. Rather, there are sensory inputs that determine the signal's timing based on the flow of traffic. The algorithm is a well-constructed, step-by-step order that directs the traffic appropriately, although it may not feel like it when you're sitting at a red light. Bus schedules. Every weekday morning, thousands of buses crisscross neighborhoods picking up students. Mapping out efficient bus routes is an overwhelming manual task to execute without an algorithm to automate the calculations and schedule the right students for the right addresses at the right time. Lesson activity. The trainer shares a sheet with a problem to be solved. The problem is about a shepherd who is planning to pass through a river by using his boat. The below cargoes: a sheep, a wolf, a grass. The transportation should be completed in safety, since the wolf might eat the sheep or the sheep Might eat the grass. The boat capacity is small, so can only pass on and only one cargo of the above. Trainers should design the algorithm. The discussion follows last 10 minutes.